Hey, hi everyone. Today let's look at the problem minimum swaps to sort. Given an array of distinct elements, we have to find the number of swaps, minimum number of swaps required to sort the array in strictly increasing order. So we have to find how many minimum swaps are required to make an array sorted in the ascending order. So given this example 2854, if you see, if we just swap 8 and 4, the array will end up being 2 4 5 8. So it will be in a sorted order. So that means you need one swap to achieve this condition of having the array purely sorted. This problem I saw in Geeks for Geeks, and this was an interesting problem, so thought of providing an explanation for it. So now first let's try to identify the intuition for the problem with an example. Okay, so let's take this case here, the previous example itself. It's 2 8 5 4, and finally we want to have this as our final output, that's 2 4 5 8. Now let's take each of these array locations and see how to handle this. So to start with, we take 2. 2 is in its proper position, so nothing has to be done for 2. Now let's take 8. Okay, so if you see 8 has to actually move to location 3. And similarly, if you see here, whatever is in location 3, which is 4, has to move to location 1. So if you actually swap these two locations, swap these two values, then you have the 8 and 4 in proper position. So that means if I have one swap, 8 and 4 will be in the proper locations. Now let's take 2, the index 2, which contains 5. So 5, as you can see, is in the proper location. So if you just have one, and as we have already taken care for this 4, so that means if we have one swap, then we are good. Okay, now as I told you, the minimum swap here is then 1. Now let's take another example. Let's take another example. Now if you look at here, this is the final thing that we want to achieve. So now let's take the index 0. Now 10 has to go to index 3. So now let's use the same approach as before. Now 3 has to come to location 0. So that means if I do a swap here, 3 and 10 will be in its appropriate positions. So we have already taken care of this location 0 and location 3. Now let's take 19. 19 has to go to location 4. Similarly, 5 has to come to this location, as you can see here. So that means another swap of 1 to 1 will give us the right positions for index 1 and index 4. Now what is remaining? So now let's take 6. 6 is in its proper position, so we don't have to worry about it. 3 and 4, index 3 and 4 we already took care. So this means that the minimum swaps we need here is 2. Okay, let's take a slightly more complicated scenario. So from this, one small intuition that we get is, if you have 2 indexes that needs to be swap. If you form a cycle with 2 indexes, then basically you will need one swap. So now let's take a slightly more complicated case where this is our array and this is our final array. Okay, so if you see here, for index 0, 2 has to move to index 1. Okay, but now let's take what is there in index 1. That is 4, and 4 has to move to index 3. Okay, now 1 is here and 1 has to move to index 0. So now only you see a cycle is forming. Okay, so that means to do this, if we form a cycle with 3 elements here, then we need 2 swaps. Let me tell you how. either I could have a case where 2 and 4 is swapped. Okay, and then what will happen is 2 will come here, 4 will come here, and then finally 1 and 4 needs to be swapped. So that means you need altogether 2 swaps. Okay, now let's move to the next element, unvisited element here. So if you see here, 5 needs to move to location 4, index 4, and 3 needs to move to index 2. So this already forms a cycle. So that means a single swap here would give me the final data. So this means that minimum swaps are needed here is 3. I believe now the intuition of this problem is clear. Now let's just jump into the algorithm here. Now let's take the above example, which was slightly complicated. So let's use that as an example and see how to come up with an algorithm for this. There are multiple ways. Okay, I'm going to go with the approach where we use an array basically. So let's try to create an array of pairs with the value and its current index in our given array. So now this will end up being 2 0 4 1 5 2 1 3 and 3 4. Okay, now let's just sort this array in the ascending order. So because if you sort this in the ascending order, these values will go to its appropriate positions. Now let's take a look at how this helps. Okay, we also keep an array visited with all its of the same size and all the values set to false. I'm not showing the values of visited here because the slide becomes very overcrowded. Okay, but I think it's clear, right? So now you have a visited array of the same size and each of its initially all the values are false because we haven't visited any nodes here. Okay, and let this be the final variable that we have to return with the count of the minimum number of operations needed to make this array sorted. Okay, now this is the core portion of our code. Now let's do one thing. What we will do is we will iterate through this array from 0 to array size -1. It should be array size -1 actually. Okay, if first we will check whether we already visited the our element. So in this case, first this is not visited, so we will come here, we will mark this element as visited. Okay, then we will first check if this element expected to be in, so in the original array, is the element in the same position as what it needs to be in. So if 1 was placed here, then we would have got 1, 0. So now you can see that the actual location of 1 is in 3. Now what happens is we will so this is not the case, so we'll come here. Now we will have to find the size of the cycle that is formed as a result of moving or swapping the elements. So that means you actually need a swapping, right? So now we have to find the cycle size needed to swap these elements around. So 1, as you can see, is currently in 3. So that means let's jump to the location 3. Okay, there 4, there the current value is 4 and it is actually pointing to 1, and so there you have 2 and that is now pointing to 0. So now if you see here, you will get this as your cycle size will be 3. So your minimum operation needed to swap these things will be 2. Okay, all right. Then now by this point, this element, this element, this element are all visited. Okay, you can see this loop, right? So you'll take J and do this iteration. Okay, and we determine the cycle size involved here, and finally we'll be able to determine the min operation. Now same thing, so now let's move to the next node. So this is already visited, so nothing happens, so we'll just continue. Then we'll come to 3. So if you see 3 also, I is not equal to array dot, it's also not in the correct location. So what happens is we'll go here, we'll jump to 4, okay, and then so that lands us to this index, and if you see here, this is 2, so this will come to this location. So now you are back to your original ith location. So this together forms a cycle. Okay, so that means one swap will give us the final data. So the total minimum operation will be 2 plus 1, which is 3, and we'll just return the min operation. So that gives us a background of the how this problem needs to be solved. Okay, now let's do one thing. Let's see how to solve this problem. Okay, I'll just do a quick coding for this problem. Okay, sorry. So let's make this full screen. Okay, now let's start as we stated earlier. We'll start with a array sorted. Okay, so we will create a vector of pairs, basically int comma int, and it's called array sort. Okay, array dot, so this will be of size array dot size. Okay, now we'll just iterate through each of the elements in the array. 0 I less than array dot size plus plus I. Okay, and array sort will be of I will be equal to, we will take the ith element and its location. All right, then what we'll do is we will now create a vector of visited elements. Okay, and we'll mark it with initially set to false. So this is to track the elements visited, and we will also have our output parameter, so we can put this as 0. Now let's do one thing. Now let's sort the array sorter. This will be our final sorted array. This is how basically our final sorted array should look like, right? Should look like. Okay, so now what we'll do is we will have array sort dot begin comma array sort dot end. So this is in ascending order. Okay, now here we are. Now we have already sorted this array. Now let's iterate through each of these elements. We will take I is equal to 0, I less than array sort dot size plus plus I. Okay, if first thing is we'll check whether this already a visited element. So visited of I, then I can just continue. Okay, then if the next thing is we need to check whether are we in the right position for this element. So if I is equal to array sort dot of I dot second. So just to give you a heads up, so first denotes the value. So this is, I think I will put it much simply. So this is in the form val comma idx, right? So let's come back. Okay, here we will check whether if this is the case, then nothing needs to be done. Element in the correct position, right? So if not, what we'll do is we'll take j is equal to I, and we can determine the cycle basically, and we will make, okay, I think I also have to mark this as visited of I equal to true. Mark as visitor. Okay, now also I have to keep track of the cycle node count. I'll just make this as 0. I prefer to do in a do-while loop, so it's much more readable. J not equal to I, because we know that we would have entered this case only if j not equal to I. So what we'll do is we will make this cycle size plus plus, because now this means even for the ith node it's a first vertex, so I'll add that one. Then j is equal to, as you can see, we will just look at the jth elements dot second. Okay, so I believe you remember that old explanation. So now what will happen is, and we will also have to mark, sorry, I think I have to do this also. We have to also mark visited j to true. Okay, now basically once we have all the we have come out of this loop, our min operations will be equal. We can just add the cycle size minus 1. Okay, and once we come out of the loop, we can just return the min op. Okay, let's see how it goes. Okay, let's compile it. Let's see. Okay, there's some mistake here. Oh, sorry, I forgot a semicolon here. Okay, just waiting for this evaluation. Yeah. As the result comes, if you see here, let's also calculate the time complexity involved in this problem. So this would be n log n. Okay, and this will be of order of n. Okay, and this also will be of the order of n. So altogether we will end up being having a time complexity. So let's put it here, right? Time complexity of order of n log n, and space complexity which is order of n, because we are using another array for this. Let's just try submitting this also. Okay, so just waiting for the result. But as you can see, it's a very efficient algorithm. I hope this explanation helps. All right, so that's it. Thank you. Have a good one.